So today we're going to look at the proposition 2 of Euclidean geometry. So in the first, in previous video, in which I talked about the first proposition of Euclidean geometry, which is that we can use a compass and a straight edge to construct a perfect equilateral. So we start at this. Given a line segment, it doesn't matter how the length, we can draw a perfect equilateral triangle just by using the straight edge and also compass. And then let's go back to here. Then find the intersect point, and then we got a perfect equilateral triangle. And today we're looking at proposition 2, and we're going to use this proposition because that is proven, so we can use it. Okay, so here is how things goes for proposition 2. So basically, we do a construction. Proposition 2 basically says that given a line segment, and we can copy that to anywhere in any orientation. And remember, the tools we have for Euclidean geometry are compass, which is collapsible compass, that if you lift it off the paper, the two legs will collapse. They will collapse and to each other, and so we cannot really using it as it is to copy a line segment, which is different from today's compass. Today's compass, we pretty much will stay put, but still you might bump it a little bit, so you still cannot be sure that you can exactly get right. And also the straight edge, it's basically a ruler without all the markings. So you cannot use it to measure the length, and you're trying to copy it. And even with rulers, when you're trying to copy the length, you cannot be perfectly exact. But with proposition 2 showed us that with a collapsible compass and the straight edge, we can construct, we can copy a given, actually any given line segment to anywhere with any orientation. Okay, so how it goes. So if, for example, if I want to copy to here, really doesn't matter where to copy it, but the construction is the same. Then what we're going to do is that we can connect these 2 points, and that's basically our postulate 1. It said that in any 2 points, we can construct a straight line. That's how we did. Then we're going to making a equilateral triangle. And so that proposition is proven, so we can use it. Now, once we made it, we can hide those circles, which are just kind of help us to do the construction. And then what we're going to do is we're going to use this point as the center of circle and use this as the radius. Basically, it is the given line segment as a radius. So another circle, and then we're going to extend this line segment, and that intersect the circle here. Then we're going to draw another circle here, and we're going to extend it to there. So now what we got, okay, I'm going to put some letter there. It's kind of very helpful. So let's see, we're going to copy this AB, and the proposition said that if we construct this way, we can copy the line second AB to, so the AB, let me do that, not this point, this line, and put in the red here. And what we construct here, from here to here, the length of that will be exactly the same as AB. Okay. So we copy that to this point, and here is our D. So here's what we're going to prove it. So first of all, when we prove Euclidean geometry, we give a statement and we give a reason. So anything we do, we have a reason for it. And so we know that the triangle E, oh, let's put this as O, okay, as kind of, because that was the center of the big circle. So the triangle BOC is a equilateral triangle. Equilateral, just write that, equilateral triangle. And which is our proposition 1, that we proved that. So that's our first statement. And second statement is that this line OE and OD, OE is congruent, like that, congruent to OD. Well, because we draw a circle. That's the definition of circle. And for a circle, the center to any point, anywhere on the circle is always constant. So the radius is constant. So OE and OD basically are the radius of the circle. So OE and OD are the radius of the same circle. So therefore, we know that they are usually like that, kind of help that. So they are the same. And then we'll find that AB actually is congruent to B. So we're talking about this line and this line. Remember, we draw the circle using here at the center and here as a radius. So therefore, this one is also radius of same circle. So they are the same. So I just kind of just pretend that I write something here to that effect. So just save some time. Okay, now what we already know is that OE is congruent, just over there, OD, and CD then is OD minus, so CD is from here to here, is the whole thing here minus OC. Well, we already know that OD and equal to OE, so it's the same as OE minus OC. OC is and OB are the same because they are the equilateral triangle. So OB and congruent to OC, that's equilateral triangle, just all the same. and OB. Now, OE minus OB is the same as BE. So we know that this length and that length are the same. But we also know that AB is the same as BE. So therefore we got this. CD is equal to BE and equal to AB. So this line CD is congruent to this line, B and E. And we also know this line is equivalent to AB. So therefore CD and will equivalent to CD and AB are congruent. So that means we copied AB to CD. Now, once we got this done, then we can easily draw a circle and just change that any direction that we want. So we can use that, and here the circle. Now, once we have a circle, we can have any direction. You could draw this way, you could draw this way, you could draw this way. They're all congruent to AB. So we basically copy that to any point and any orientation. So basically we're saying this, we copy down to here, and because we can draw a circle, and then we can move that this way, we can move that way, we can move that way. It doesn't matter which orientation that you want to do. So basically this population shows that given, as long as you have a compass and a straight edge, we can copy a line segment to anywhere in any orientation, and not just roughly the same. We're talking about exactly the same. So that is power of Euclidean geometry. So everything in the Euclidean geometry is exact. All right, I'll see you next time.